All right, in this video, we're going to go over perpendicular bisectors and triangles. A couple things that we need to know. Perpendicular bisector theorem. All right, a point on a perpendicular bisector of a segment if and only if it's equidistant from the endpoints of a segment. So basically what we're saying is if I see these markings that mark up a perpendicular bisector, okay, then any point on this line will be equidistant to the two endpoints. So since, let's see, is line CD is perpendicular bisector of AB, then, right, something like CA and CB are going to be equal. So any point on that line. So you could have a point down here, E, let's say, and because E is on that perpendicular bisector, E is also equidistant to the endpoints. Now, a couple other things that we're going to introduce in this chapter are points of concurrency. Point of concurrency is a point in which three or more lines intersect. In triangles, they have special names. We're going to discover 4 points of concurrency: the circumcenter, incenter, centroid, and orthocenter. We'll split those up over multiple days. If you want to get a brief glimpse as to what they are, picture here kind of shows you each one of these points is the respective point of concurrency. And you can see their markings here as well, kind of lightly. So the first one that we're going to go over is the circumcenter. So if you create the perpendicular bisector for each side of a triangle, where those perpendicular bisectors intersect is the circumcenter. So when I take a look at this particular picture here, C is the circumcenter. All right, the reason why I know that, well, I can see this is a perpendicular bisector. This green segment is a perpendicular bisector. So is this green segment perpendicular bisector to this side, and then this green segment here is a perpendicular bisector. Now, the nice thing about circumcenters is that they are equidistant to the corners of the triangle. So what that means is because we know that that's the circumcenter, this segment and this segment and this one are all equal to each other. So it's also the center of a circle that circumscribes the triangle, meaning that circle just touches the corners. And you can see the circumcenter, which is P in each one of these pictures, can be inside the triangle, on the triangle, even outside of the triangle. So don't get thrown off. Points of concurrency aren't always inside the triangle. Now, some examples, how we can use some of those properties to solve. So for instance, on this one, right, I immediately notice that we've got a perpendicular bisector marked. So we know that WX is a perpendicular bisector then, right? It is marked. So therefore, any point is equidistant to the endpoints. So this segment should equal this one. So our setup to solve this guy is then 2x plus 11 equals 4x subtract 5. And again, that's by the perpendicular bisector theorem. And then we would go ahead and solve. Taking a look at this next problem here. All right, solving for x. All right, don't overthink it. We see a perpendicular bisector. It also will tell me that these two pieces are going to be equal to each other. So we just go ahead, set them equal to each other, and solve. Now, both of these first two examples are about level 2s of a question. All right, here's about a level 3. Line OQ is perpendicular bisector of segment MP. Does the point L lie on the perpendicular bisector? All right. Now, if you were to try to justify by, say, drawing and extending the line, that doesn't hold as enough weight as referencing a particular rule, right? Because I will tell you that it'll be oftentimes that pictures are not drawn to scale or things are too close to call. So we need exact measurements to make a determination. So how do we know that L is on it? Well, we notice that L is the same distance as it is from P to M. They're both 15 here. So because L is the same distance as it is from M to P, we know by the perpendicular bisector theorem, L must be on the perpendicular bisector. So all right, taking a look here, finding a circumcenter of the triangle. So remember that a circumcenter is where the perpendicular bisectors meet. So if I notice here, I can try to figure out where the perpendicular bisector is for two sides of this triangle, and then where the intersection is of those perpendicular bisectors would be the circumcenter. So I'm going to pick the two nice sides of the triangle. I'm going to pick out this horizontal side. I'm going to find its halfway point. So 5 is its length, so about 2.5 here. Okay. And then perpendicular slope. So the slope of that line is 0/1. So perpendicular would be 1/0, negative 1/0. So I'd go down 1. And so this would be the perpendicular bisector to that side. Okay, rough estimate. And then I would take a look at the other side here. Right, halfway point there would be this point. And because that's let's see, the slope of that line is 1/0. Perpendicular would be 0/1. So there's our perpendicular bisector. The intersection point lies right here. That looks to be about 3.5. That looks to be about 3.5, 2. Right, same idea here. Right, we've got a right triangle. Right, I'm going to pick out the horizontal and vertical sides of it. So here I got my horizontal side. I'm going to find its halfway point. And then I'm going to go up. Actually, I'll probably go down because the slope here is 0/1. And so that will get us 1/0 as our slope, negative 1/0. So here's the perpendicular bisector. And then for our vertical side, find that halfway point. 1, 2, 3, 4. Half of 4 is 2. And then because that's a vertical line, has a slope of 1/0, I'm going to go with negative 0/1 as our slope. So there is the perpendicular bisector. And our circumcenter lies at negative 2, 2. Now you might encounter problems like this. So which point is the circumcenter, right? So again, remember circumcenter is where the perpendicular bisectors meet. So I'm going to want to try to find a side where I know we got a halfway point. So if I take a look at side AB, I can see that S is halfway because I see these markings here. And I've got a perpendicular line to it. So I know that that for sure is a perpendicular bisector. If I look at a C, W is not marked as a midpoint, so I'm not so sure about that one. Let's go to the other side here. BC looks like Z is going to be our midpoint. Okay, I know F here is kind of misleading, but then we got Z with a box too, so then we know that that is our perpendicular bisector. So that tells us then where those two lines will meet. Following it looks like they're going to R then. R is going to be the circumcenter.